For f of x equals 9 over x minus 8 and g of x equals 8 over x, find the following composite functions and state the domain of each. We want to find f composed with g composed with f composed with f, and g composed with g. So let's start by finding the composite functions. For part A, we want to find f composed with g of x. Now this operation of composition is an operation that means to substitute one function inside of the other function. So if we know that, we can rewrite this notation to help us have a better understanding of what we're doing. The function that is on the outside is the one that's written first, and the one that's after the composition is the one that is inside. So we're going to write this as f of g of x. Notice that the g is inside of the function f. And that's how we're going to find this composite function, is by substituting the function g into the function f. So if we do that substitution, we would have 9 over 8 over x minus 8. So we've replaced that x with 8 over x. We're going to simplify this expression now that we've done the substitution. And this is a complex fraction, a fraction inside of a fraction. And there are a few different ways you can go about simplifying this. One way would be to get a common denominator in the bottom here. It would be 9 over 8 over x minus 8x over x. So what I did is I multiplied by x over x to get that common denominator. This gives 9 over 8 minus 8x over x. And now I'm going to rewrite this division. The fraction bar means division. I'm going to rewrite that division as multiplying by the reciprocal. So we're going to get 9 times x over 8 minus 8x. And we'll multiply straight across, multiplying fractions. You multiply numerator times numerator and denominator times denominator. And that gives 9x over 8 minus 8x. Now, I just want to show you one other approach that we could take. We have 9 over 8 over x minus 8. Another technique for simplifying this would be to clear fractions. When you clear fractions, that means you want to get rid of these smaller denominators. And to do that, we're going to multiply by x over x. That would give 9x in the numerator. And in the denominator, we would distribute this x to both terms. When we distribute to the first term, the x's cancel and we get 8. And when we distribute to the second term, we get minus 8x. We get the same expression with these two different methods of simplifying. So then we want to state the domain of this composite function. Now typically we would find the domain of just our final answer, but in this case, because we have these individual functions to consider, we have a little bit more work to do. So let's start by finding the domain of these individual functions, and then we'll talk about what the domain of this composite function is. So f of x is 9 over x minus 8. This is a rational function because we have a variable in the denominator. And for rational functions, we want to exclude any values of x that will cause the denominator to be 0, because division by 0 is undefined. So let's set that denominator equal to 0 to find our restricted value. So we set the denominator, x minus 8, equal to 0. We're going to solve by adding 8 to both sides, and we get our restricted value to be 8. The domain is all real numbers except for 8, so we can write that in interval notation. Or if we want to write it in set builder notation, we can say x such that x is not 8. So we're excluding 8 from the domain, but including all other real numbers. Okay, we were going to do the same thing with the function g of x. G of x is x over 8, which is a rational function. We'll set that denominator equal to 0 to find the restricted values, and this time 0 is our restricted value. So we can write that in interval notation. It's negative infinity to 0, union with 0 to infinity, or in set builder notation, x such that x is not equal to 0. That gives the domain of these individual functions. Let's talk about the domain of our composite function, f composed with g of x. Now, to consider our composite function, we have to first think about substituting into g of x. That is the inside function, and so we're going to start with excluding 0. So x cannot equal 0. And then we can look to what we got in our final expression here to get any other exclusions. We're going to take 8 minus 8x, set that equal to 0, and solve. We subtract 8. That gives negative 8x minus equals negative 8. Divide by negative 8, and we get x equals 1. So we also need to exclude 1 from our domain. So in our interval notation, we want to exclude 0, and we also want to exclude 1, but we're going to include all other numbers on the real number line. So that gives us a domain of negative infinity to 0, union with 0 to 1, union with 1 to infinity, or in set builder notation, x such that x is not equal to 0 and x is not equal to 1. Okay, let's continue by finding our other composite functions. This time we're going to find g composed with f. And once again, this notation means this notation of composing or operation of composing is substituting one function inside the other. The one before our symbol is the outside. The one after our symbol is the inside. We're going to have g of f of x. So we're going to take our function f of x and substitute it into the function g. This will give 8 over 9 over x minus 8. I'll treat this division, this fraction bar, as division, and we'll multiply by the reciprocal to simplify. That gives 8 times x minus 8 over 9, which is 8x minus 64 over 9. Now thinking about domain, we're going to start by excluding any values of the inside function. So we found earlier that 8 is a restricted value for f. And then we're going to look at our final answer to see if we get any more restricted values. Since I don't have a variable in the denominator, I'm not going to get another restricted value. So the only restricted value is 8. So the domain is negative infinity to 8, union with 8 to infinity, or in set builder notation, x such that x is not equal to 8. Okay, let's try f composed with f. F composed with f is f of x. So we have f on the outside and f on the inside. So we're taking 9 over x minus 8, and we're substituting that in for x. That gives 9 over x minus 8 minus 8. And we can simplify this by clearing fractions. We'll multiply by x minus 8 over x minus 8. So I multiplied by this little denominator here. That will give 9 times x minus 8 over, we'll distribute in the denominator. When I distribute to the first term, the x minus 8's cancel, and when I distribute to the second term, I get minus 8 times x minus 8. Now I'll simplify. I've got 9x minus 72. And 9 minus negative 8x plus 64. That's 9x minus 72 over negative 8x plus 73. But now we want to find the domain. We're going to start with any restrictions from our inside function. And we can see that 8 needs to be excluded. And then we get any restrictions from our final function. So let's set that negative 8x plus 73 equal to 0. Subtract negative 73. That gives 8x equals negative 73. Divide by negative 8. We get x equals 73 over 8. So 73 over 8 is equal to 9.125. I wanted to figure that out because I wanted to know if 73 over 8 was less than or greater than 8. And I need that for my interval notation. So my domain is negative infinity to 8. Union with 8 to 73 over 8, union with 73 over 8 to infinity, or in set builder notation, x such that x is not 8 and x is not 73 over 8. Okay, we've got one more to go. Let's find g composed with g. So g composed with g of x is g of x. G is our outside, g is our inside. So we're taking g of x and we're substituting it in for x. That will give 8 over x. This is 8 times x over 8, which is x. We want to take a look at any restrictions from our inside, and restrictions from our inside are 0. And look to see if you have any restrictions with your final expression, and there are none. And so we just have that one restriction. The domain here is negative infinity to 0, union with 0 to infinity, or in set builder notation, x such that x is not equal to 0. On this example, we have the question for f of x equals square root x and g of x equals 7x plus 3. Find the following composite functions and state the domain of each. I'm going to find f composed with g composed with f composed with f, and g composed with g. So let's start with f composed with g of x. This operation of composition means substituting one function inside of the other function. The function before the composition symbol is our outside function, and the function after the composition symbol is our inside function. So we can rewrite this as f of g of x. So this indicates to us that we're going to substitute our function g of x inside of f of x. This will give us square root of 7x plus 3. We also want to find the domain. So let's talk about the domain of the individual functions to start with. F of x is the square root of x. This is one of our even root functions. And we have a restriction that we only want to work with real numbers. So when we calculate the square root of negative numbers, we get complex or imaginary numbers. Square root of negative 1 is I, which is a complex number. So we're going to restrict the expression inside the radical to being greater than or equal to 0. So that gives a domain of 0 to infinity. In set builder notation, that would be x such that x is greater than or equal to 0. The second function, g of x, is 7x plus 3, and this is a linear function, more generally a polynomial. And the domain of every polynomial function is all real numbers. There are no restrictions on that domain. So we say negative infinity to infinity. Now, when we find the domain of our composite function, we always start with the inner function to see if it has any restrictions. And we just stated that it does not have any restrictions. So then we're going to look at our final function here. And that final function has an even root. So we want the expression underneath the radical, 7x plus 3, to be greater than or equal to 0. I'm going to solve this inequality, and it'll lead me to the domain. So I solve by subtracting 3 on both sides. That's 7x is greater than or equal to negative 3. I'm going to divide by 7, and this gives x is greater than or equal to negative 3 over 7. So we have a domain of our composite function, f composed with g, being negative 3 over 7 to infinity. Let's try some of our other examples. We want to find g composed with f of x. This is g of f of x. Notice this, that is before the composition is our outside, and after the composition symbol is our inside. So this time we're going to substitute square root of x into 7x minus 3. That gives 7 square root of x plus 3. We're going to start with any restrictions on our inside function. Our inside function is square root of x. And we already saw earlier that x needs to be greater than or equal to 0. Then when we look at our outside function, 7 square root of x plus 3, we don't have any restrictions there. So we have a domain of 0 to infinity for this one. And in set builder notation, that's x such that x is greater than or equal to 0. Okay, we've got 2 more to go. We want to find part C, f composed with f of x. That's f of x. This time we're taking square root of x and substituting it into square root of x. That's square root x. Now this notation may seem a little bit strange at first, but if you remember that radicals are the same thing as exponents, we can write this as x to the 1/2 power to the 1/2 power. One of our properties of exponents is that we can multiply these powers together when we have an expression to a power raised to another power. So this gives x to the 1/4 power, and that is the same thing as the 4th root of x. So we want to find the domain. We'll always start with our inside function. Our inside function has a domain restriction that x needs to be greater than or equal to 0. When we get to our final answer here, we have the same restriction that x has to be greater than or equal to 0. And that's because we're taking the even root. So we have a domain of 0 to infinity, or in set builder notation, x such that x is greater than or equal to 0. Okay, one last example, g composed with g. G composed with g of x is g of x. And we want to take 7x plus 3 and substitute it back into 7x plus 3. That will give 7 times 7x plus 3 plus 3. To simplify this, we can use the distributive property. That gives 49x plus 21 plus 3. That's 49x plus 24. We want to find the domain, our inside function. 7x plus 3 is a polynomial function. There are no restrictions on that, and there are no restrictions on our final composite function. So we get a domain of all real numbers, negative infinity to infinity. On this example, we want to evaluate each expression using the values given in the table. So let's examine the table first. We're given x and a list of x values. We're given f of x. Remember, f of x is the same thing as y, so we're given a bunch of y values. And we're given g of x, and g of x is the same thing as y, so we're given another set of y values. So one set of y values for f, a different set of y values for g. In part A, we want to find f composed with g of 1. So this operation here is composition, and this operation is where we substitute one function inside of the other function. The function that's before our composition symbol is our outside function, and the one that is after our composition symbol is the inside function. So this is the same thing as f of g of 1. Now, if we focus on the notation that we have inside, we have g of 1. That notation, g of 1, is giving us a value of x is equal to 1, and g of 1 is referring to a y value. So we're going to focus on having an x coordinate of 1 and the y value associated with that for the function g. So we know that g of 1 is 0. So we can simplify this now. We know that g of 1 is 0. And then we can focus on the notation f of 0. We know that x is equal to 0, and f of 0 is referring to the y value. So to simplify this, we're going to go on our table where we have an x of 0, and for the function f, find that y value. So f of 0 is negative 1. And we have our evaluation. F composed with g of 1 is equal to negative 1. Here we have a few more to do. So let's take a look. So in part B, we want to find f composed with g of negative 1. This is f of g of negative 1. And on my x, I have negative 1, and my y is 0 for the function g. I have f of 0, and here I have an x of 0, and I want to focus on f. F of 0 is negative 1. Let's try another one. In part C, we have g composed with f of negative 1. This is g of f of negative 1. Let's focus on f of negative 1. F of negative 1 is negative 2. G of negative 2, let's use a different color there. G of negative 2 is 2. Okay, I'm just taking a look at what I wrote down on this previous example here, and I think I need to correct that. F of 0 is negative 1. Okay, so part D, I want to find g composed with f of 0. This is g of f of 0. I'm going to erase a few of my markings here. Let's find f of 0. So I'm looking where x is 0, and also looking where I have f. So my y value is -1. So now I have g of -1 and g of -1. Here's where my x is -1, and g is this row. So g of -1 is 0. Here we have a couple more. Part E, g composed with g of -2. This is g of -2. So g of -2 is right here, an x value of -2, and this last row are my y's for the function g. So g of -2 is 2. G of 2 is right here, and x of 2, and my y's for g. So g of 2 is 2. And let's try our last one, f. F composed with f of -1. F composed with f of -1 is f of -1. So here is f of -1. We have the x value of -1, and these are all y values for f. So f of -1 is -2. And f of -2 is going to be right here, -4. And so we've got our answer. F composed with f of -1 is -4. The surface area S in square meters of a hot air balloon is given by S of R equals 4 pi r squared, where r is the radius of the balloon in meters. If the radius is increasing with time t in seconds, according to the formula r of t equals 2/3 t cubed, this is for time greater than or equal to 0, find the surface area of the balloon as a function of the time. So we're given two formulas. We're given a surface area formula. Surface area is 4 pi r squared. And we're also given a radius formula. Radius with time as a variable, that's 2/3 t cubed. And what we want to do is we want to have surface area with a variable of time. Now, since our inside variable for surface area is radius, we're going to be able to use composition to build this. So we're going to be able to substitute our radius function inside of the surface area function, and that would give 4 pi times 2/3 t cubed squared. This is 4 pi, and we're going to apply this exponent to both of these factors. That's 4/9 times t to the 6th. That's going to give us 16/9 pi t to the 6th power. So now we have our surface area where the variable is time. Thank you for checking out my videos. Have a great day.